My dear students, so this topic is going to be very interesting. See, beta, we all know how a capacitor is charging, but here I'll discuss a very interesting phenomena or very interesting property जो आपने शायद observe नहीं करा होगा. So let me first confuse you, or give you the context of this mystery or the kind of thing I'm going to discuss here. So see this figure on the left side, we have a capacitor C with a resistor. So this resistance is actually the net effective resistance of the circuit, right? Okay, now you are charging it through a battery V. So once it is fully charged, finally the energy stored in the capacitor in the form of electric field is half QV. Work done by battery, because it is taking charge from the left plate to the right plate to the left plate. So this is the total work it is doing. So only half QV is getting stored, and this QV is the total work done by battery. The rest of the energy is lost due to this resistor. It is actually generating heat energy, right? Correct, we know this thing. But what happens, see this right side dollar figure, what happens if I don't consider any resistor? I mean, ideally you can imagine this like, okay, you can say, so the wire will have some resistance. So better I'm taking ideal case where either you imagine a superconducting wire wala case, or just think about, I mean, the overall resistance of the circuit is going to be very less in this case, right? Now you are charging it through a battery having same potential. So finally, this is the energy stored in the capacitor, work done by battery. But the question is where that heat loss, I mean, I will not say it as heat loss, just simply say it as loss. So where is that loss of energy is going, and how to explain this? This question better definitely आपके mind में आया होगा when you are studying this RC circuit or charging of capacitor. So let me discuss this problem. हम थोड़ा सा deep dive करेंगे इसमें, and definitely you'll get a very good answer after this. So before going ahead, let me discuss this RC circuit, not in a detailed version, but just a quick, overview. So Q as a function of T over capacitor is given by Q max, then 1 minus e to the power T by RC. That is how charge is growing. And at steady state, which is T tends to infinity, you can say the charge is, it is reaching to a maximum value, this Q value. So finally it is going to have this energy, half Q into V. How to find out loss? So if I calculate loss, it is like I square R dt, that you integrate 0 to infinity. And how to find out I here better? So this is Q, you can directly get I from here. That is how current through a resistor is changing. I equals to dq by dt. So this will be Q minus e to the power minus t by rc into minus 1 by rc. So it is q by rc e to the power minus t by rc. This directly you can put it here, and what you will get finally, that this is actually equals to half q v, right? So once it is reaching in steady state, that is the loss. अच्छा, यहाँ पर एक और इंटरेस्टिंग चीज आपको समझ में आनी चाहिए. What about the case when you are not, I mean, you're not still reached to that maximum charge wala state? Basically you are in your transient phase. So there are two states better, transient phase and steady state. Transient phase, it is the case, I mean, the time zone where the charge is, the capacitor is still in the charging mode, right? So for that we can say one thing, this, the rate at which battery is doing work, it is, it is getting stored in the capacitor, plus there is some rate of heat loss. So this is important for transient phase. That's it. So once it is in steady state, equal, like half it is storing and half the circuit is losing as heat. Before reaching steady state, the battery is doing work at some rate. Some part of it is going into store. I mean, it is going to store in the capacitor, and some part of it is going into as a heat loss. And they are not equal. They are not equal. I mean, this and this, they are not equal. Their sum is actually equal to this. This is basically an energy conservation principle, right? That's it. Okay, now let us come back to our actual problem. Suppose in the circuit I'm not putting any kind of resistance, or ideally you can imagine, or practically if you want to imagine, you can choose a wire which is having almost zero resistance, right? Now what happens in this case better? First of all, because of zero resistance, we can say the current value will rise very abruptly. Why? Because if you see this case previously, see this, for t tends to 0, the current is maximum. I mean, we already know this case. So for any capacitor, t tends to 0. I mean, the instant when you're just, starting to charge this capacitor, exactly at that moment, the capacitor is behaving as a short circuit. So the circuit is going to have maximum current. But that current is actually limited by the value of resistance, right? So here, what will be the current at t equals to 0? V by R. But what about this case? Here, R tends to 0. So basically, I will tend to infinity. So there is a sudden burst of current in the circuit, right? Now, since there is no resistor, and finally you see the total charge over capacitor is CV, and the energy it is storing, that is half Q into V. So where that half is getting lost, I mean, I'm not able to understand. The capacitor is still, it is having the same electrostatic potential energy. तो ये लॉस को आप यहाँ पे कैसे एक्सप्लेन करोगे, दैट इज द मेन क्वेश्चन. सो हाउ टू अंडरस्टैंड इट, इसके लिए बेटा थोड़ा सा अपने को some extra things we need to understand. Beta, you remember that Maxwell law, better to say Faraday law, in your class 10th, or I mean, if you haven't done this topic, this actually related to AC or electromagnetic, and even connected to EMI, electromagnetic induction, right? But let me just give you idea in a very simple manner. So if you remember that Faraday law, what it says, if there is a change in suppose in space we have magnetic field lines, and suppose any hypothetical loop, so if there is a change in magnetic flux with time, that will generate EMF. So EMF is proportional to this thing, right? So if you change the magnetic flux, technically it will generate electric field. So let me discuss in very simple way. So phi is representing the total number of field lines through a given loop. So if you change it, suppose d phi by dt is not equal to 0, so it will generate electric field. Okay, it will generate electric field. That is what Faraday law says. But reverse, is it correct? Yes. If there is a change in electrostatic flux, if it is non-zero, it will generate B, magnetic field, right? Same thing is happening here. So उसके लिए अपने को you have to see this capacitor. So what you will do, बेटा ये जो portion है ना between these two parallel plates, you have to focus here. You have to actually zoom in this portion. Okay, so that is the actual story, like what exactly is going on here. You can understand this way. So suppose the charge over capacitor is Q, and it is growing actually, right? Although in this case, the charge over capacitor, it's growing almost instantly. In previous case, because of resistance, it is taking some time, but here it will grow instantly. But in general, let me discuss the case. So suppose the capacitor is having Q charge at some instant, positive Q and negative Q. So there will be some electric field strength in between them, right? Beta, you can easily imagine it. Now suppose if I imagine any arbitrary surface, I mean, you can imagine like field lines are passing through it. So what you will see, that d phi E by dt, total value of electrostatic flux, definitely it is changing with time. It's not equal to 0. Why? Because Q is increasing with time, right? As a result, sigma will increase. And we know electric field का strength between these two plates is sigma by epsilon naught. So electric field is also increasing. If that is increasing, the flux is also increasing, right? If this is the case, it will generate B, magnetic field, right? So technically what is happening in between the plate, this activity, change in electrostatic flux, it will generate magnetic field, and you can say they are actually generating electromagnetic wave, because this is how any electromagnetic wave is generating. So you can imagine any charged particle, if it is accelerating, so in surrounding of that charged particle, the overall field strength is changing, so electrostatic flux will change, that will generate magnetic field, and the change in that magnetic flux will generate electric field. So basically they both are generating each other, right? So finally, in short, what is happening during the charging of capacitor between these two plates, because of these fluctuations in the field, electromagnetic radiation is arising, EM wave, right? And this is not even, I mean, it's not, you know, uh, hidden or not hidden, I mean it's not packed within the capacitor, it's actually going out of it, right? So even if I take a compass, magnetic compass near to this capacitor, it will show deflection. Even you don't need to put it inside these two plates. Even if you place it outside of the plate or near to the plate, it will show the deflection. So basically these EM waves are generating in between this between the plates, and they are even going out of the plates. So that is basically, you can say, loss in the form of EM waves. Better to say radiation. Better to say radiation. Now again, अभी भी confusion clear नहीं हुआ बेटा? Why? If that is the case, तो ये तो यहाँ पर भी होना चाहिए, because capacitor is charging, its charge is growing. See, dq by dt, q is a function of t, so sigma will be a function of t, e will be a function of t, then flux will be a function of t, right? So why we are not getting such loss? So basically in that case, the loss should be more than this half qb. No, that's not a correct way to think about it. See, first of all, beta, this loss is actually dependent on, better to say, this sorry, magnitude of loss is proportional to, actually, rate, better to say rate, magnitude of rate of change of field. They say, as I said, this, if electrostatic flux is changing, it will generate magnetic field. Basically B is actually proportional to this. So larger the rate of change, how to get it? When there is large change in electrostatic flux, so that will generate more strength of magnetic field, and hence that electromagnetic wave का strength. So basically this magnitude of loss is proportional to rate of change of field, right? और उसमें भी this rate is actually further depending on uh, the value of flux, right? See, in above case, what is happening? Definitely charge is changing with time, but this resistor is kind of controlling that increment in the charge. So even if you calculate d phi e by dt, still that is non-zero, but in comparison to this heat loss due to resistor, that is almost negligible. So practically, if you study this circuit, I'm damn sure the overall heat loss will be greater than delta H. But the thing you can say that electromagnetic wave radiation wala loss is almost negligible in front of heat loss due to this resistor. The dominant form is given by this resistor. But in our case, the second case where we are not choosing any resistance, so what is happening? There is a sudden burst in current because resistance is zero. A sudden burst in current, it's like the capacitor is charging almost instantly. It is getting the whole q charge in all of sudden. So just imagine the burst of electric field you'll be getting here. It's like at particular instant there is no electric field, and the very next instant you are getting a huge electric field, right? So this d phi e by dt is going to be huge. It will actually tends to infinity. Why? Because I tends to infinity, right? So there is a huge burst of radiation within the plates or around the plate, right? So it will lose a lot of energy, and that loss, if I calculate, it is equals to half qv, right? So in this case, the loss is primarily happening because of this EM radiation, and in the above case, the loss is happening mainly because of resistor. So ये mystery यहाँ पे खत्म होती, but there are still many questions. The question is, I mean the further question, if this radiation wala loss is dependent on this current, I mean since it is growing very fast, so radiation burst यहाँ पर आएगा आपका. So even if I further reduce the resistance, see I have taken R tends to 0 here, maybe practically 0 now, but I'm taking it almost 0. But suppose if I take it exactly 0, which is totally ideal case, so this current will be further maximized, and then the rate will be further more. So loss तो और ज़्यादा होना चाहिए था. Why this loss is limited? Why this loss is limited? And that is very interesting thing. मतलब loss होता है ठीक है. You can say, if I take a resistor, the radiation loss is negligible, the heat loss is maximized. धीरे धीरे आप resistance को कम करना शुरू करो, what will happen? Now resistor is also generating heat, and there will be some loss because of loss because of that radiation, right? So both are there. Slowly further, if you decrease the resistance value, that loss due to radiation is going to dominate. So basically it is shifting from one way to another, but in either way, either by resistor or by this uh, mm, radiation part, the heat loss is limited. The heat loss is limited. Why it is limited? You should ask yourself why it is limited. Because the energy change, because the energy change in capacitor is also limited, half qv or half cv square, right? So the fact is capacitor, if you are charging it through a potential v, it cannot take more energy than this. So capacitor का energy fixed है, I mean whatever energy it will take finally, it will hold finally, that is fixed. तो बची हुई जो energy है, it has to go into loss. ठीक है, अब यहाँ पे एक और क्वेश्चन ये आता है, सो हाउ कैपेसिटर is actually getting this much energy? I mean, is there any way to charge capacitor such that there is no loss at all? I mean, there is no resistor, no radiation ka loss. So in that case, will it still get that half qv? I mean, will there be this half factor there? Is there any way to charge a capacitor in such a way, right? So let us discuss that also. So yes, we have a way in which we can charge a capacitor कि loss वहाँ पे आए ही ना, not even through the resistor and not even through that radiation. For that, you need to recheck the basic definition or the derivation to get that half qv or half cv square. You remember that derivation better? So what I will do, I'll not choose any battery, because battery, it will consume some of the energy, because if any battery is there, it is taking charge from one plate to another. So you can say like every battery has some internal resistance, so it will lose some, it will consume some of the energy. So I'm not choosing any battery here. So imagine there is some external agent. Suppose that external agent is me, and what I'm doing, I'm taking charge from one of the plate and I'm depositing it over another. So basically I'm taking charge from here to here. Now don't ask how I'm getting charge, but yes, and assuming this external agent is doing work in such a way that there is no loss. So simply it is taking charge. Let's suppose dq by dq amount it is putting from one plate to another. And let's suppose at some instant of time it is charged positive q and it is negative q, right? At that particular instant there is already electric field existing between the plate. So basically what is happening, first time when you are shifting that charge, you are not doing any work. But once, I mean after that, every next transfer of charge is happening through this field. You are actually going opposite of the field, so you have to do the work. Now what is that small work done? So you have a potential difference between these plates, which is q by c into dq, right? So what is total work done by that external agent to charge this capacitor? So 1 by C, it is Q dq 0 to Q. So it will be Q square by 2C. Q square by 2C. Now in this case, you can say sir electric field तो यहाँ पर भी है, flux तो यहाँ पर भी change हो रहा होगा. So in order to omit that, we can imagine the situation like I am shifting this charge in a very slow manner. Slowly आपने छोटा सा dq charge transfer किया, then wait for some time, then again you are shifting this dq. So the rate of change of charge over the capacitor, and hence the rate of change of electrostatic field, and hence the electrostatic flux, it is very slow. So basically this d phi e by dt, that is tending towards zero. So there is no involvement of external battery here. There is no involvement of this radiation. So now you got that battery is storing q square by 2c. So finally, when it is getting that q charge, let's suppose v is the potential difference across it. So you can also write it as half q into v. Now, what exactly this telling to you? But a capacitor in any situation, whether you connect it with battery or whether there are any type of losses, the final energy stored by capacitor is half qv or q square by 2c. तो कैपेसिटर का जो एनर्जी स्टोरेज है, it has nothing to do with those losses. In short, capacitor is not demanding any energy loss, beta. Capacitor is not demanding any energy loss. It is solely dependent on the fact how you are charging the capacitor, right? See here, you can observe this thing. You're shifting the charge, and the potential delta v between plate, it is slowly growing. It is slowly growing. पहले क्योंकि ये है ना बेटा, potential difference between the plate. तो धीरे धीरे क्यू आपका बढ़ रहा है, तो पोटेंशियल डिफरेंस बिटवीन द प्लेट इज स्लोली स्लोली इंक्रीजिंग. दैट इज हाउ अ कैपेसिटर इज चार्जिंग, राइट. बट बैटरी के केस में क्या होता है, नाउ यू विल अंडरस्टैंड इट क्लियरली. इफ यू कनेक्ट अ बैटरी, what is happening, if you connect a battery, the battery, right from the starting, right from the starting, it will try to give a potential difference, it will try to generate a potential difference V across it. So capacitor के across potential slowly slowly increase होता है, we have seen it above, right, Q by C. But the battery is trying to push the charges, all these charges, right from zero charge up to Q charge, the whole, I mean each and every bit of this charge is getting pushed at V. So you can imagine it this way better. Suppose you have a tap, right? Suppose you have a tap. इस टैप में से जो वाटर की ड्रॉपलेट्स आती हैं, दे आर फिक्स्ड. लाइक फर्स्ट सेकंड में वन ड्रॉप, सेकंड सेकंड में, फर्स्ट सेकंड में वन ड्रॉप निकला होगा, सेकंड सेकंड में टू ड्रॉप, फिर ऐसा थ्री ड्रॉप. द टैप इज डिजाइन दैट वे एंड एवरी ड्रॉप हैज some particular volume. But there is a pump outside of it, it is pushing lot of water into it, and the water which is coming out of tap, it is already defined, it is increasing in a fixed rate. So that extra push generated by the pump, what will happen? It will actually make this pipe to blow up, right? So battery सारे चार्ज को V पोटेंशियल पे पुश कर रहा है टू द कैपेसिटर, टेक इट, बट कैपेसिटर इज नॉट टेकिंग that much potential at a single instant, that is slowly growing, right? So battery is applying or using more energy to charge the capacitor, but capacitor is taking that charge at a different rate. तो बेटा कहीं ना कहीं तो वो लॉस जाएगा, energy conservation principle, right? So if resistors are there, primarily resistance तो वहाँ पे है ही, and then this radiation part is also there, right? So in short, capacitor is never, I mean it's not, I mean it's never demanding any kind of loss. Capacitor बोलता नहीं है कि मेरे को charge करने के लिए you have to go through loss. It is the way how we are charging the capacitor. So I hope you understood this topic, right?
So practically, is there any way to charge the capacitor to get almost zero or minimize losses? Yes, it is possible, and it is called adiabatic charging. How to achieve it? See, the battery was the main problem, right? It was causing more energy losses. So you can do one thing. Instead of battery, you imagine a constant current source charging the capacitor. As you can see in this figure, uh, with constant current source, the voltage and charge over capacitor is increasing linearly, right? So in such cases, and one more thing, you're not connecting any resistor also, so there is no heat loss. Now with this constant current source, you have to imagine one more thing, that current value should be very less. A very feeble current is charging the capacitor, correct? Why we are taking this condition? See, for any higher value of current or just a normal value of current, the charge over capacitor is changing at some rate, right? And that will further change the electrostatic flux. So in order to minimize that rate of change of flux, which is actually responsible for the radiation generation, so better to have a current which is very weak. So it's like it will become an adiabatic process, just like in thermodynamics, and where you are using a reversible process like that, you have to imagine it, right? So in such way you can achieve a capacitor charging with almost zero loss. We cannot minimize it better, because see, every circuit has some non-zero resistance that is there, and even if you take very less value of current, still there will be some part of energy going into radiation. And also during the charging of capacitor, some energy is getting lost near the boundaries of the capacitor. So there are many factors which will affect the energy loss, but yes, in this way you can minimize you can minimize the energy losses, and you can have an efficient charging of capacitor. And this I'm giving a name, adiabatic charging of a capacitor. That's it.